Okay, we're going to be looking at the root test now. The root test is a test that works especially well for series involving nth powers, and that's because we're going to be taking the limit as n goes to infinity of the nth root, and so the nth root and the nth powers will ultimately cancel out. So what the root test says is that if the nth term, if the limit as n goes to infinity of the nth root is less than 1, then we know, that's right here, then we know that this is going to be a convergent series. If the nth root, the limit as n goes to infinity of the nth root is greater than 1 or infinity, which of course infinity is greater than 1, in both cases that will tell us that the series diverges and that it's an inconclusive result if the limit is actually equal to 1. Hopefully this makes sense, because if the terms themselves are less than 1, if the nth root terms are less than 1, this will likely make the terms get smaller, and so it makes sense that it will converge. Okay, let's look at some examples. Okay, in this example, a sub n is e to the 2n over n to the n. We can view this as e squared over n all raised to the nth power. Viewing it as something to the nth power will help us later when we simplify. So let's set up our limit. So we have the limit as n goes to infinity of the nth root of our expression e squared over n all to the nth. And so we have that the nth power and the nth root will cancel. And so we're really just looking at the limit as n goes to infinity of the absolute value of e squared over n. So what happens as n goes to infinity? Well, the numerator is just a constant, right? E squared is just some number, and so as n goes to infinity, this goes to 0. So by the root test, this tells us, since this is less than 1, that this series converges. Now in this next example, we actually have an alternating series, so you can also use the alternating series test. Here I'm going to use the root test just to show you that it can work. So we can write this as one term to the nth power, which will help us for the root test. I should point out here also, since this is an alternating series, I didn't explicitly write it in the root test, but if the series does converge by the root test, it will converge absolutely. So just like with the ratio test, getting convergence it's implied absolute convergence, so you don't have to check for conditional convergence. Okay, so let's set up our limit. Again, we see that the nth root and the nth power will cancel, and again this limit will be 0. And since 0 is less than 1, that tells us that this series converges absolutely by the root test. Let's look at another example. Again, let's write it as one expression all to the nth term. Okay, so note that we're left with a 2 to the negative 1 here, so we have this whole expression to the nth term. Now let's set up our limit. As usual, our nth root and our nth power cancel. Again, this is why the root test is so nice for expressions when we have nth powers. And so we get the limit as n goes to infinity of 2n over n plus 1. Notice that I used a property of negative exponents here to write the 2 in the numerator. So this is a linear term over a linear term, and so this rational function as n goes to infinity goes to a limit of 2. Now 2 is greater than 1, so this tells us that our series diverges by the root test. Okay, as we do more examples, what I would encourage you to do now is to try these examples on your own and then watch me after you've paused it to see if you got the same answer as me. Okay, I'm going to skip over this first one since I already did this one. Let's move on to B. So we can set up our ratio. And so we see we have a rational expression with the numerator being third degree if I were to cube the numerator, and the denominator also being third degree if I were to cube the denominator. Of course, this would not just be 3n cubed plus 1 cubed. We'd have to do a lot of expanding out. But the ultimate, the bottom line is that the leading coefficient would be cubic in both places. And also note that this is an alternating series, but this negative is going to go away because we're taking the absolute value. So the limit will just be 2 cubed, right? Would have been negative 2 cubed, but so since that's absolute value. So 2 cubed, which is 8 over the leading coefficient down here would be 3 cubed, which is 27. 8 over 27 is less than 1, so this series converges, and because it's alternating, it actually converges absolutely by the root test. Okay, let's try some more examples. So after canceling the nth root and the nth power, we're left with the limit as n goes to infinity of 2, nth root of n plus 1. Now this nth root of n, you can also think of it as n to the 1 over n power. So what happens as n goes to infinity? Well, if you don't know what happens to the limit as n goes to infinity of n to the 1 over n power, or the nth root of n, you should see number 25 in the packet above, where we showed that the nth term as n goes to infinity, so we showed that the limit as n goes to infinity of n to the 1 over n is actually equal to 1. And the way we did that was using the sort of natural log trick, as we called it in class. So as n goes to infinity, this expression goes to 1, so the whole limit goes to 2 times 1 plus 1, or 3. Since this is a value greater than 1, this tells us that our series diverges by the root test. So now as we try to do the next problem, notice that it's not already automatically written as something to the nth power. So the root test may not be your first natural choice, but because I have this n in the denominator, this nth power in the denominator, it's still a possibility. So let's look and see what happens. We see that once we set up the limit, we can actually just write this using properties of radicals. We could just divide the radical over the radical. So that means in the denominator I will get the expression to cancel, but in the numerator I'm still left with this limit. So again, we're stuck with trying to evaluate the nth root of something with an n plus 1 in it. It's very similar to this last example, except instead of with an n, it's n plus 1. If you did the same techniques we did in number 25 earlier in the packet using the natural log sort of trick, we would get the exact same process. And so in fact, and you should do that, you should pause and check that, you will actually get 1 in the numerator here. So this limit actually goes to 1/3. This tells us that our series converges by the root test. And if you didn't like using the root test, just think about the fact that there aren't many other choices. You would not want to integrate this, for example, using integral test. You might try a comparison test, that might be another possibility, but it's not geometric, it's not a p-series, so we need something more powerful. So the root test actually worked. Okay, we have 2 more examples. When I look at this one, I see first of all that it is something to the nth power, but rather than using the root test, actually notice that this is just a geometric series. It's just geometric where the base is 1/e. So what does that tell us about our series? It of course tells us that it's a convergent geometric series. If you wanted to apply the root test to this, you'd see that it would still work. You'd cancel out the nth root and the n, and you'd see that the limit as n goes to infinity would just go to 1/e. So you'd get the exact same result. Okay, let's look at this last example. We see that this limit goes to 2, which is greater than 1, so this diverges. If you'd like to see more examples, please see these other YouTube videos.